Hello kids, this is Mrs. Butcher and this video is on graphing and writing the equations of absolute value functions. The absolute value parent function is just y equals the absolute value of x, and you guys should know that the absolute value means the positive value basically because it's the distance away from 0. So if we were to graph the absolute value of x, it would look just like this. Okay, so I'll start with 0. The absolute value of 0 is 0. The absolute value of 1 is 1. The absolute value of 2 is 2. So on the right, we have a line with a slope of 1. But then the absolute value of negative 1 is 1. There. And negative 2 gives us 2. There. And so on. We get a line on this side with a slope of negative 1. So we can write this as a piecewise function. We'll say f of x equals, and then we're going to put this bracket, this big bracket, because we're going to write two pieces of this function. And the left piece is the line y equals negative x. And that's for the interval of all x's from negative infinity, see it's going on negatively that way, up to 0. So you can write that in interval notation or inequality notation. Most often you'll see it as an inequality, so we'll say x is less than 0. Then for this right-hand side, that line is y equals x. And that is for the interval of 0 on up to infinity, which we'll say x is greater than or equal to 0. And I put an equal to on this because one of these has to have an equal. If they were both not equal, then there would be an open circle in the middle there. And if they were both equal, then they would overlap and it wouldn't be a function. So it doesn't matter which one you pick, but you just have to pick one or the other. So that's called a compound function. However, we don't have to write it like a compound function because we can write it as y equals the absolute value of x. And now, just as a quick review, let's talk about some of the things that we've talked about in the past, like domain and range. I'm going to use a D for domain. And our lowest x value over here is negative infinity, whereas our largest x value is positive infinity, and there are no breaks. The range for this function, the lowest y value we have is 0, and it does touch the 0, and then it goes out infinitely up. Okay, if I asked you for the x or y intercepts, well, let's see, our x-intercept. That would be the ordered pair at 0, 0, wouldn't it? Or x equals 0. And that's also our y-intercept, 0, 0. Symmetry. We have y-axis symmetry here, don't we? And let's see, do we have a maximum or a minimum? It has a bottom, so we have a minimum, and that is at 0, 0. It's increasing from 0 to infinity. And remember, we don't put hard brackets on our increasing or our decreasing. And it is decreasing from negative infinity until we get to 0. Okay, so now let's graph some other ones. And when we do, we're going to refer to our general transformation formula. Remember, the A is your vertical stretch or compression. The B is your horizontal stretch or compression. That C is your horizontal shift, and the D is your vertical shift. And so the function in this case, the f of, is our parent function, absolute value of x. And you should write these down if you don't remember them, but if you do remember what A, B, C, and D do to your function, then you don't have to write it again. So here's an example. We're going to graph y equals negative 2 times the absolute value of x minus 3, and then all plus 5. So if we think about what the transformations are going to be, we know that to my x values, all I'm doing is going right 3. So that means I'm going to add 3 to all my x values. My y's are going to change 3 different ways. I have a negative here, which reflects it over the x-axis. I have a 2 here, which is going to stretch it by a factor of 2, and then I have a plus 5, which is going to shift it all up 5. So there's a few ways you could graph this. One way you could graph this is to lightly sketch in your parent function and then just do these things to it. Shift it right 3 units, take all your y's and reflect them to the bottom, stretch them by 2, and then shift them up 5. That can be a bit time consuming though. You could also just make a table of your parent function, x and y. So if we went with -2, 2, -1, 1, 0, 0, 1, 1, and 2, 2, I know all my x's are going to have 3 added to them. So I could make a new side and just write x plus 3. Oh, I didn't want to move that. X plus 3, sorry. So if I just added 3 to all my x's, -2 plus 3 is 1, -1 plus 3 is 2, 3, 4, 5, like that. And then I could make a new y, and my y's I'm going to have to reflect them all over the x-axis means I need to multiply them all by a negative and stretch by a factor of 2. So I'm going to multiply all my y's by -2 and then add 5. So if I did -2 times 2, I'd get -4 plus 5 is 1. 1 times -2 is -2 plus 5 is 3. 0 times -2 is -2 plus 5 is 5. And then once again, -2 times 1 is -2 plus 5 is 3, and -4 plus 5 is 1. So then I could plot the green points, and I would have my new function. And another way to do this, once you get used to seeing how it repeats the same every time, is just think, okay, your vertex is going to move from 0, 0, right 3, and up 5. So my vertex is now going to be at 3, 5. So I could just plot that point. And then I know that the slope on the right used to be +1. And then if you look at whatever's in front of the x, that's going to be the new slope, -2. So I could go down 2 and over 1, down 2 and over 1, and I could draw that line. And then I know that the other side of my absolute value is just a reflection of the right side. Basically, it's got a slope of +2 from this point. And so I could sketch that in like that. So either way, I've plotted 1, 1 right here, and 2, 3, 2, 3, and 3, 5, and 4, 3, and 5, 1. Either way you want to do it is great. And if we wanted to talk about the domain and range of this function, our domain is still all real numbers, so -infinity to +infinity. And our range, if you look at the range, it is now pointing downward. The lowest y value we can have is -infinity. But it has a top, it has a maximum, and that is at 5, so -infinity to 5. And since we do actually touch the 5, we'll put a hard bracket. So let's try another one of these just to be sure we know what we're doing. This time I've stuck a b value in there. And remember, when you have a b value, you have to factor it out. So we'll take the absolute value, and then I'm going to take this 2 with a parenthesis, x plus, and then if I divided 2 out of that 2, it would really be 1. And then -3 stays the same. So for this graph, we know that this 2 right here is our horizontal compression because it's greater than 1. So we'll say we have a horizontal compression by a factor of 2. We know that this +1 is our horizontal shift to the left 1 unit, and the -3 takes it all down 3. So you could take the parent function and do each of these 3 transformations to it. You could take the x and y chart and make sure that you multiply all your x's by 1/2, and then take away 1, because remember we do the opposite with the x, and then take all your y's and subtract 3. Or you could say, well, I know that my vertex is going to go left 1 and down 3. So my vertex is going to go from 0 to 0 to -1, -3. And then I know the slope is 2. So I'm going to go up 2 over 1, up 2 over 1, and so on. And there is going to be your absolute value function. And now, because it won't let me go back and just record over my mistake, I now have to correct my mistake at the end of this section. But the thing is, when we do a horizontal compression, we're not going to say by a factor of 2. We're actually going to say by a factor of 1/2. So we'll scribble out the 2 and we'll put 1/2. You always want to go ahead, see, we multiply all our x's by 1/2, so we want to call our compression by 1/2. So it's always the reciprocal of that number right there. Always the reciprocal. Just like, mentally we knew if it compresses by 2, then it's multiplying everything by 1/2. But we want to actually say horizontal compression by 1/2. And that's my correction, sorry. All right, now moving on, we're going to talk about how to write the equation of an absolute value function if I give you the vertex and then some other point that's on it. So what you're going to do is take the general equation, and then when we do this, there's 2 different cases because I didn't tell you what A and B are. And because we're multiplying by 2 things, A and B could be a number of different numbers. So when you solve a problem like this, you will be told to assume either that A equals 1 or assume that B equals 1. So let's try it first by assuming A equals 1. All the numbers they gave us fit into this equation because the vertex -3, 5 is going to be our C value because we're going to go left 3, and then our D value because we're going to go up 5. And sometimes you've seen this as H and K instead for your vertex. So I know that C is -3 and D is 5. And then if I give you a point, I've given you an X and a Y. So I'm going to plug it in with 6 for my Y, or my G of X. A is 1. B we don't know yet. X is -1. Minus -3 will be +3. And then plus D, so plus 5. So now I have everything filled in except the letter B. So now I can just work some math magic here real quick. Take away 5 from both sides. I get 1 equals the absolute value of B times -1 plus 3, which is going to be 1 equals the absolute value of 2B. And so the absolute value of 2B has to be 1, so 2B equals 1, or -1, B equals 1/2, or -1/2. And because our vertex is going to be in quadrant 2, so you look at -3, -5, and you go, okay, well -3, 5 is over here. We're just going to go with the positive value of B. And so now we'll rewrite G of X, I'm going to use blue, sorry, G of X equals, and then A was 1, so I'm not going to write anything, absolute value of B 1/2, parenthesis X minus C, so X minus -3 is X plus 3, and then plus D, so plus 5. And you don't have to multiply that 1/2 out, you don't have to distribute it, you're just done. You can put a box around your answer and you're happy. All right, now this time we're going to find the equation of the same function, but this time we're going to assume that B equals 1. If you recall, our vertex was -3, 5, so the -3 is our C, and the 5 is our D, and then the point -1, 6, that would be our X and our Y, same as we did last time. Only this time we're going to take our function Y equals, so 6 equals, and then this time we're going to let A be the thing we find. And we're going to let B just be 1. So 1 times, and then we've got X minus C, so we've got -1 minus -3, and then plus D. Well, absolute value of that, and then plus D, plus 5. So if we do all this work, we have 6 equals, and 3 plus -1 is 2, and 1 times 2 is 2, so we have A times 2, and then plus 5. So we're going to take away the 5. 1 equals 8 times 2. Divide by 2. A is 1/2. So when we write this one, we're going to say Y equals, or f of x equals, or whatever. And then A is 1/2 on the outside. Absolute value of x minus C, so x minus negative, so plus 3. Plus D, so plus 5. So this one looks a little bit different than the other one that we did because the other one had the 1/2 on the inside and this one has it on the outside. But both of those equations will give you an absolute value function with a vertex at negative 3, 5 that passes through the point negative 1, 6. Okay, finally, I want to do a word problem. I want us to formulate an absolute value problem out of a real-world situation. So 2 kids are passing a ball between them. If Joe passes the ball from a height of 1.4 meters and it bounces 3 meters away from him, where should Mo stand to catch the ball at a height of 1.2 meters? So let's draw a picture of this. Okay, because I'm the best artist in the world. Here's Blue Joe with his ball at 1.4 meters. He's bounce passing it, means it's going down, bounces 3 meters away from him, bounces back up at the same angle, and Mo standing here wants to catch it 1.2. So where should he stand? So we'll let this be X. So we're saying how far away from Joe, right? X can be our distance from Joe. All right, what are we going to do? Well, we know we have a absolute value function. These guys are going to have the same slope. So we know our vertex is at 3, 0. Well, if this was an equation, that means it's shifted right 3 and not vertically shifted. So we know the vertex is at 3, 0, or so H will be 3 and K will be 0. So what we know is we've got our equation, y equals A, absolute value. We're going to let B be 1. And then we need x minus 3, and then we need plus nothing, right? So we just have y equals a, some a value times the absolute value of x minus 3. And we just need to figure out what a is. So we do exactly like we did when I gave you a point. And see this point right here? We know that point. That is at 0, 1.4. So I'm going to use that as my x and y. So y is 1.4, x is 0, and then we don't have a k, so that's it. So 1.4 equals a times the absolute value of negative 3. The absolute value of negative 3 is 3, so 3a. All I need to do now is divide 1.4 by 3, and I have an a value of 7 over 15. But I didn't ask for the a value, I just need that to get further in this problem. So my equation I now know is y equals 7 over 15, absolute value of x minus 3. And I want to figure out what this x is when this y is 1.2. So what I'm going to do is just put that 1.2 in for y and solve for x. So 1.2 equals 7 over 15, absolute value of x minus 3. So the first thing I'm going to do is multiply 1.2 by 15 over 7, which is 18 over 7 if I use my calculator. So 18 over 7 equals the absolute value of x minus 3. So I'm going to do plus or minus x minus 3. Okay, I'm going to need to scroll up for a second. Hold on. All right, so 18 over 7 equals x minus 3. Add 3 to 18 over 7, and I get 39 over 7, or 5.571. But I also have to solve 18 over 7 equals negative x plus 3, right? Because I have to do the negative of both of them. So if I subtract 3 from 18 over 7, I get negative 3/7 equals negative x. So therefore x is positive 3/7, which is the same thing as 0.429. And now you're thinking, why do I have two answers? Why are we saying that Mo could stand in two different places, and intercept that ball at 1.2? And that's because he actually could. You see, at 0.429, that's right here. We'll say that's right here. Because the ball's going down, and at that point, it's a 1.2. He could stand right there before it even bounced off the ground, and he could catch the ball at 1.2. But we're assuming that the ball bounces and goes back up. So this would be the second one that we got, the bigger one, which is 39/7 or 5.571. So that's the one that makes more sense in the context of this problem. So when we answer the question, if we're assuming that the ball did actually make its bounce and then bounce back up, then we've got to go with the bigger one. So where would he stand? Ew, I made a mess of that. That's okay. Where would he stand? Mo should stand 5.571 meters away from Joe. And that's the answer to our word problem in a nice, complete sentence with units and 3 decimal places and all that other good stuff. So that's the end of this video. You guys have a great evening, and I'll see you tomorrow.